All right, guys. Let's begin. Today we're going to be discussing sound. Hello. Today we're going to be discussing sound. Chapter 15. I don't know how we managed to catch up with physical science in the chapter. I don't know. Just magic. Huh? It's a mystery to me. Oh, y'all are not seeing the right thing. No. Okay, sound. Yeah, and the video is sound. Today what we're going to be doing is going through and kind of defining sound. We'll talk about some of the characteristics of sound. What now?
Is the mic on the video? That would be ironic.
If it wasn't. Today we're talking about sound, but you can't hear me. No, I guess it's on. We'll find out. And also kind of dispel some of the incorrect previous teachings of sound. A lot of books teach sound a little bit, frankly, wrong. So we're going to go through and kind of correct that. So real quick, let's go through a little bit of review. We've already gone through this. Sound is a mechanical wave, guys. Therefore, since sound is a mechanical wave, every mechanical wave is going to require a medium. Okay, so sound does require a medium in order to travel. Okay, most typically that medium is going to be air. Okay, but sound can travel through different media. Mediums is medium-I. I think it's media. I think yes, media. So, for instance, it can go through steel. It can go through water. The only thing it cannot go through is space, empty space, or a vacuum. Yeah. Okay. So the whole thing in space, no one can hear you scream is absolutely correct. Sound is a compressional mechanical wave. Okay. Therefore, since it's a compressional mechanical wave, that tells me that the particles are going to move parallel to the wave motion. Okay? Okay, so they're going to be moving parallel to the wave motion. So if the wave is moving to the left, then I know the particles are vibrating left and right. They're not vibrating up and down. Okay, in a transverse wave, they'd be vibrating up and down. What was the other name for compressional wave? I only mentioned this once. I don't know if anybody remembers that.
We'll start with
Longitudinal.
Yes.
Okay. And since sound is a compressional wave, anytime air particles compress, the pressure increases. Okay. So I know a sound wave, in definition, is going to be a series of high pressure and low pressure areas. Okay, just variable air pressure.
So like words are really air pressure?
Yeah.
These words are kind of like...
That's
sick, man.
Okay, so sound waves are a little bit tough to visualize because you can't really, you can't see air particles. That's slightly problematic. But if we could see a sound wave, we'd see something like that.
What word is he saying?
Okay, so sound waves, guys, have areas of high density air called compressions. Okay, remember any compression wave has this, and it has areas of low density air called rarefactions. Okay, typically air would just be at 1 psi, right?
Yeah.
Okay, so essentially, if I had a psi meter and the sound wave was coming by, it might say 1 psi, 1.5 psi, 0.5 psi, 1 psi, 1.5 psi, 0.5 psi. Okay, so that pressure sensor would just be changing. Now, that would be a very extreme, not psi, I'm sorry, atmosphere. That would be an extreme high, 1.5 atmospheres. It does. I mean, a sound wave doesn't typically have that high of amplitude, but I guess it's theoretically possible. But if we could see a sound wave, we'd see something kind of like that. Okay, it's almost kind of like pulses you would see spreading out. Okay, so what you should see up here is kind of in circles. You see areas where the particles are really close together.
Yeah.
Okay, that would be the compressions. And you see the areas where the particles, like right here, are more spread apart. Okay, that'd be the rarefactions. Okay, so if that object in the center were creating these disturbances, you would see these pulses kind of spreading out. Okay. So in terms of a sound wave, and if I was looking, if there was a speaker and it was making a sound wave and I could see it, we'd see something kind of like that.
Like you drop
Okay.
it in the water.
Kind of, I mean, but you know, water's moving up and down.
Yeah.
But similar look. You actually can see sound waves, and let me. I can't believe I hadn't thought to show y'all a video of this. Let me pull it up real quick. This is too good to not show you. Well, no.
Or some blood.
Oh, that's something different.
That's in the lab.
That's for physical science. Have y'all ever seen some sodium in water?
Yes.
It explodes and it's
No, go back to the beginning.
yeah, it explodes.
Did you record this?
It's sideways, but
Did you do that experiment in here?
no, that was in the whatever it's called, chemistry lab.
It's under the food thing, right?
Yeah.
Oh.
Yeah,
Oh,
yeah.
okay, I see.
Okay, I can't remember what this would be called. Let's see if we can see one, and I'm just kind of.
Have you ever heard of? I think it's called a Rubens tube. No, a Rubens tube. It's supposed to be. Have you
Mhm.
ever heard of? I think it's called
I
a
saw it
Rubens
online.
tube.
Rubens tube.
Or Rubens something. It's like
Movie
it's like
2K because Tom told me about it.
it's like a pipe that you can like, and it has like candles in it. And then if you run sound waves through the actual PVC like pipe chamber, it'll like it'll replicate like the waves and the frequencies and stuff like that.
The Hershey store? Oh yeah, Pennsylvania.
In the fire.
Well, to be honest, now my computer's frozen. Should have just continued with the lesson. It was too cool not to show you, but I guess I'm not going to show you. I'm probably not going to show you the PowerPoint now either. It's all right. Well, maybe it'll stop taking a break eventually. We'll come back to that later.
It worked. It worked.
What? No, that's not the video. I'm getting the pinwheel, the little rainbow pinwheel. Yeah. It's starting to become quite the common occurrence.
Oh really?
Yeah.
Explain to users.
Yeah, user error. Anyway, sometimes in explosions, I don't know if y'all have ever seen video that I can't. It's not working, but you'll sometimes see like right outside of the explosion, almost like you can see that line of the sound wave moving. Okay, that's because it's a very high density. It's a part of the air. It's the compression from that sound wave that's extremely high density and it's causing light to bend. Okay, so that's the reason you can see that it's bending light, because it's very high density. All right, so I've entitled this one "Sound Waves: The Right Way and the Wrong Way, the Counterclockwise Way." Okay, so the way sound is typically taught is this the higher picture there. And so when I was in school, I thought, sound waves, I guess particles moving up and down, sounds traveling. And even if you look back at the poster in the back, you see these waves, but there's a blaring omission. Okay, and the blaring omission is that they don't tell you what that is. Okay, I look at that and I assume that's particle movement, but that's not particle movement. Okay, that's a graph. Okay, I mean right here. Okay. On what I have up here, we have a graph. Okay, over there that's just a drawing. Okay, so sound is really not accurately drawn using a sine curve. Okay, now the pressure due to a sound wave can be accurately drawn using a sine curve. But not particle movement. Okay, if I'm actually drawing out particle movement, I'd need the bottom picture. Okay, so in terms of particles, I have areas of high density particles, so this would be air particles close together. I have areas of low density those are spread out. And when the air particles are close together, that gives me high pressure. Okay, so what I have here is I have a graph of high pressure at that point. And then when they're more spread out, that's lower pressure, and so it's graphing lower pressure there. Okay, so when you're seeing this, that's not a graph of particle movement. That's a graph of pressure. And you were probably taught before, this is sound. Sound looks like this. The graph pressure of sound looks like that. That makes sense? That plagued me for a long time. And the same thing is going to happen with light. When we go to graph an electromagnetic wave, it's going to be like mystical. But it's really not like moving this way and something's crazy happening, but it's really not as mystical as it seems. Okay. So the speed of sound. The speed of sound is going to count on one thing. Okay, the only thing that influences the speed of sound is the medium that it travels through. Okay, so let's first talk about the things that do not influence the speed of sound, or the speed of any wave. How loud the sound is does not influence how fast the sound goes. Okay, a quiet sound travels at the exact same speed as a loud sound. Okay, so you can whisper and you can shout and we hear it at the exact same time over there, assuming we're close enough to hear a whisper. Okay. The second thing that does not influence the speed of sound is the pitch, or what it sounds like. Okay, so an opera singer doing some shrill stuff travels at the exact same speed as the bass. Okay, that's the reason why you're at a concert, when you're far away from the speaker, the sound doesn't really get distorted all that much, because all that sound is traveling at the same speed. Okay, so how loud it is, what it sounds like, that does not affect the speed of sound. Okay, what does affect the speed of sound is the medium. Okay, so things about the medium that can affect it. The state of matter. Okay, so if it's solid, liquid, or gas, that affects the speed of sound. Okay, the pressure of the medium. Okay. As you change the amount of pressure inside of the medium, typically gases, then that will also change the speed of sound. And then the last thing is temperature. Okay, temperature will affect the speed of sound as well. But notice all those things are products of the medium. Okay, as the medium is changing, the speed of sound is changing. So if you change the temperature of the medium, if you change the pressure on the medium, if you change the state of matter of the medium, it's all about the medium. Okay, general rule, guys. Solids are the fastest, gases are the slowest. Okay. So sound travels the fastest in solids, the slowest in gases. At air, at standard pressure, and you can put this on your equation sheet under, let's see, where's that? We put V equals F lambda on the equation sheet, didn't we?
Yes.
Number 36? Okay, good. Alright, so you can put that under V equals F lambda. And leave yourself a little space because we're going to put a second thing under the notes of V equals F lambda. Okay, so speed of sound in air at standard pressure is 343. You can write 343 in air at standard at STP. Okay. 343 meters per second in air at STP. Okay, so looking at this rule, what does sound travel faster in, air or water?
Water.
Water. Okay, and in fact, it travels right around 4 or 5 times faster. What is? We'll get there in a second. Okay, something like iron, that'd be the fastest. That's the reason why they say if a train is approaching, you put your ear down to the railing, and you can hear you can hear the sound of the train approaching.
Are you stupid?
Huh? Well, I mean, I'm not. When I say approaching, I don't mean like. I don't mean like it's the distance between me and you approaching. I mean like. No, trying to detect if there is a train approaching in the far distance. I do not. No. Don't lay your head down on the rail in front of an oncoming train.
I can hear it.
Look at that train approaching. I wonder if it's approaching. Well, obviously, guys, through which medium is the sound of the train going to get you faster? Through the air or through the railing? Through the railing. In fact, it's about 10 times faster. Okay. And then the next one, this one seems backwards of the other one. But the colder the matter, the slower the wave is going to travel. Now, as y'all know, solids are typically colder than liquids. Okay, so that seems backwards of what we would typically expect, or what we would expect from the first rule. But the colder it is, the slower it's going to go. Here's my thought on that. The way sound travels is by transferring energy from particle to particle. Okay, so obviously it can do that faster if the particles are closer. And the particles are closer in a solid than they are in a liquid. Okay? However, the other thing that matters is how fast the particles are moving. So if it gets colder, the particles are moving slower, so it's not going to transfer the energy as fast. Okay, so it's kind of like they offset. Sure, they're closer together, but it's slower. But even a cold solid is going to transfer sound faster than a hot gas. Okay, but not at absolute zero, but whatever. Okay, so if we were to graph that out, maybe if I were to graph out water. Let's get this little bugger going. Bugger, it's a ladybug. Okay, whatever. It's a ladybug.
Oh,
okay, so if I were to graph this out, guys, and put temperature and speed. Let's say we're graphing out the speed of sound in ice. Maybe we'll put 0 degrees Celsius there. The temperature of melting ice. We'll put 100 degrees Celsius here. So that'd be the temperature of turning into gas. What we would see is the speed of sound would increase as the temperature increased. Okay. However, when it went from a solid to a liquid, we would see a drastic decrease. Okay. Then it would increase again as we went from liquid to gas. Drastic decrease, and then increase again. That makes sense? Those might be kind of curvy, but we're. I'm just kind of giving you an approximation here.
I thought you said the speed increases as temperature increases.
So here's the temperature increase and the speed increasing. But then when it goes from a solid to a liquid, it decreases.
Oh, okay.
But then it increases some more as the temperature increases. Okay? Huh? Makes sense? Okay. Okay, I want to emphasize again that the sound of the sound does not influence the speed of sound. Okay? And one quick thing, when sound does change mediums or media, when sound does change media, it changes speed. So if sound goes from air to water, it would change speed. However, the pitch of the sound doesn't change. Okay, so therefore the frequency doesn't change. So what does change? The wavelength. Yeah. Okay, so since the speed is changing, what is always going to be changing there is the wavelength. Okay.
What do decibels measure? I'm sorry.
Decibels, that's amplitude or volume, and we'll get there. I think maybe.
What medium is sound traveling through, like through the TV or over the telephone?
Sound is not traveling through the telephone. Well, digital signals are being sent there. So essentially, you speak into the telephone, the microphone picks it up, it turns that into an electrical signal. Okay. That electrical signal, your phone then turns into ones and zeros, and that sends that to the, well, not the satellite, but the, I mean, you don't have a satellite phone, to the tower, and then the tower sends the ones and zeros over to the little communication center, and it says, oh, where's this supposed to go to? And it sends that to the next tower, wherever the other person is. And that tower sends the ones and zeros to their phone, and their ones and zeros say, oh, I need to make the...
It does that, so the ones and zeros include your, like, pitch of your voice?
Yeah.
No, that's not a good word.
That's
That's not one of those phones.
Like, when I listen to myself on a voicemail or something, my voice sounds really different.
Yeah.
Ones and zeros.
Ones, it's not actually ones and zeros. I mean, it's not like it types it up into a Word document and sends some ones and zeros. I mean, it's a signal. It's a series of pulses of on and off, and we let one be on and zero be off, and so it's kind of like it's almost like Morse code. You know, kind of like just the on would be one and the really, really fast. Yeah. Yeah, that's a byte. So anytime you download something that's 100 kilobytes, that'd be 100,000 bytes. So every one or zero would be 1 byte, no, 1 bit, and there's 8 bits in 1 byte. So 100 kilobytes would be 800,000 ones and zeros.
So many certain ones and zeros can, like, get
So for instance, yeah, well, an image typically is like, what, 4 megabytes? And so that would be 4 million bytes, which would be 32 million ones and zeros for an image. So that's a lot of information. So your phone, if you email somebody a picture, it emails them 32 million ones and zeros in 3 seconds. What is it now? What's the rate? If you send 32 million ones and zeros in 3 seconds, you're getting things a little complex. Just distance over time. It's just ones and zeros over time. Okay, we already said that. Echoes. I'm glad somebody got that. An echo is caused anytime a sound bounces off of a substance and reflects. Okay, so obviously an echo is not caused if a sound travels through something, so air doesn't typically echo in and of itself because air is not reflecting the sound, it's allowing it to travel through. And certain substances don't make echoes because they absorb sound. Okay, so an echo is caused anytime sound is reflected back. The way I think of an echo is I have a compression wave coming in, coming in, right? Okay, if it's coming in towards me, that compression wave hits my chest. Okay, so now I have high pressure right here. So what's my chest going to do? It's going to, it's going to get pushed in a little bit. Or if it comes in and hits the wall, that's going to get pushed in just a little bit, right? Well, then that has built up elastic potential energy. So it causes it to bounce back out. Well, when it bounces out, that causes a compression, which makes sound go back the other way. Okay? That's the way I think of it. I don't know if that's right or not. I think that's right. We use echoes for a lot of things. One thing that's very common is called echolocation, using echoes to figure out distance. So since we know the approximate speed of sound in a medium, let's say I shoot some sound through air, and it takes 0.5 seconds for me to hear the echo. Well, using the speed of sound, 343, and the time, 0.5, I can figure out the amount of distance that sound traveled. Okay, so if you have like a megaphone, you go, ah, and you hear how long it takes to come back, then you can approximate how far away something is. Make sense?
Unless you have bad ears. Like somebody else heard it before you did because you have bad ears. Then you'd give them all distance.
Well, I would hope that if we're going to be doing a scientific experiment, we would rely a little bit more on the quality of someone's ears and reflexes to hit a timer. Maybe a microphone would be the best method. And I think we need to try that. I'll come up with huh?
That'd be awesome.
Yeah, I'm gonna have to try that and see if we can get that nailed down. Okay, so echolocation. A lot of animals use it. Bats use echolocation to get kind of an approximate image of what's in front of them. I mean, obviously, if they go eee and they hear, they hear something, they hear a quick echo in the left ear, then they know something's close on the left. And if they hear a long echo in the right ear, well, they know it's kind of clear to the right.
Are you sure they just don't do the formula?
They probably do.
Yeah.
As
we've learned, most animals are physics majors.
Yeah.
Like the prairie dogs.
Yeah, the prairie dogs and the bats. Those physics animals. We good on echoes, guys? One thing, if you do calculations with echoes, you would need to take the distance and divide by 2, right? Because it goes there and it comes back. So if you want to know how far away it is, you need to take that distance and divide by 2. All right, guys, grab a partner, talk it out.
Yeah. Thanks for that one. It's the pressure. It's actually yeah, we're good. Alright, I heard somewhere that a duck's black doesn't echo.
Because it's the pressure.
No.
I have just proven that, but I've just read that somewhere.
Don't believe her.
No.
Yeah.
Well, I just think
I'm dating a French model.
I think typically you probably wouldn't typically hear a duck's quacking echoing because you wouldn't typically be in a place where you would hear an echo with a duck.
Remember, so I walked into Sean's house and all I saw was
I mean, unless you're in like a stadium with a duck.
bonjour.
I mean, because if you're in a lake, you don't typically hear much of an echo.
Yeah.
And if they're flying over you, then you're the object that they would be echoing off of. So for a duck, I'm sure a duck hears a duck echo. I just doubt we hear ducks echo very much.
You should like take some ducks out to a mountain.
Well, just get a duck and go to the stadium and squeeze it.
Yeah.
Um,
There we go. I heard
it echoes. Number 1, where do you think it's easier to pass the speed of sound in an airplane? High altitude, low altitude?
High.
What do you think, guys? Give me your reasoning.
I read it wrong, so.
Guys, where is it colder? High altitude or low altitude? High altitude. Okay, so where do you think the speed of sound is lower? High altitude. Okay, so the speed of sound would be lower at higher altitude because it's colder.
Wait, so it'd be easy. So what's the answer?
So it'd be easier to pass the speed of sound higher than lower because the speed of sound is lower. The higher you go, the lower the speed of sound is.
Like the higher you go.
Yeah.
Oh, okay.
So to surpass the speed of sound, you want the sound to be low. I mean, the speed of sound to be low.
I don't understand that question.
Have you seen that episode of Mythbusters where like they try to break windows by like having a jet fly really really close to some old shack in the desert?
I saw that one.
No.
It took them like 4 tries to do it because nothing would break at first. And so I think they ended up trying to get the plane closer to the ground, and then finally everything blew up.
They also tried launching missiles at it, and that was really effective, huh?
It's usually how they solve this.
Yeah. All right, number 2.
They just get busters.
Do you think our ears can pick up sound directly from a solid?
Yes.
No. Okay.
What the heck?
You just said we could listen to
You
it.
just told me about my head.
Guys, if you put your ear up to a piece of metal, does the piece of metal go all up in your ear and all the way up to your eardrum? No. What is typically in there? Air. Okay. So in order for you to hear anything, our eardrums are best suited for picking up from air. Okay, so if in order for you to hear something, it's got to transfer from wherever it is to the air to your eardrum. That's the reason why we don't, huh?
Even if it's like that.
Yeah, even if it's that, I mean, it's got to go through the air.
That's frustrating.
What if you what?
What
if you what?
I've never got
Like when you touched the Q-tip to your eardrum, that would be, that would not be a good idea.
I don't understand why they call it
What
I
if?
love it, baby.
Oh, goodness.
Oh, yes.
And we, guys, I ran out of time. These 2 example problems are easy. I'll just kind of walk you through them. A sound wave's traveling through water at 1,400 meters per second. It has a frequency of 5,000 hertz. That means V equals 1490 and F equals 5,000. Solve for lambda. V equals F lambda. Bam.
Wait.
V equals F lambda. Okay, on the second one, you're sitting on one end of the stadium and the speaker's on the other. If you're 100 meters from the speaker, what will be the delay in hearing the sound and seeing the presenter's mouth move? So you know the presenter's mouth moves and you hear the sound, okay? The speed of sound is 343. The distance is 100, so V equals D over T. Okay, so the time ends up being 0.29 seconds.
But do you divide 100?
It'd be 100 divided by 343. Ends up being 0.29 seconds.
Why would you divide 100?
100 by 2. Because it's not an echo. Not an echo. Okay, guys, homework tonight, page 405, practice problems. And I put up there also for homework, read.